3 volumes.
Yes, yes.
And we have an enormous amount of a large amount of big scientific news. And we are preparing a summary, a shorter summary than the 3 volumes to distribute around.
Yes.
And also with the outcome of this meeting. And in addition of that, I hope to the topic are very vast, because in a certain sense, what is going on is that 50 years of research have matured and given previously unexpected results. And they were topics that were highlighted already in the 71, in the last century, 1971. But as you will find hard to realize, but realize with joy, is that in the last months they are becoming effective. And I will summarize 7 of these topics at the end of this today meeting. But with reference to Stanford, I have to say that your continued attention at AUI has been extremely helpful. And I will plan to visit you later in the weeks to signify what we can do also together in the future. And at the same time, of course, the presence of Francis is still active. We will consider eventually to relieve him from some duties, but before I will see him. And at the same time, the collaboration with Stanford has been incredibly fruitful, because, as you know, Stanford was the basis for the data of Fermi-Lat, which has allowed since the foundation of ICRANET, we have been looking at this data. And even today, in the highlights, we'll present some of the data from the Fermi collaboration, and from the data of in the JEV of LAT, which, as you know, was a collaboration with the Italian Space Agency for the detectors. And this is, you will see in the highlights, we will show a very, very important GRB of observed in 2024 in the month of September last year, the 25th. And bit by bit, I would like to tell you why we feel so happy about these results. Well, on one side, in 71, January 71, I made a paper in Physics Today, which I'm sure you have seen, in which we introduce with John Wheeler the concept of black hole. Well, it has been extremely long to make of that paper a reality. In that paper, we introduce many concepts. In particular, that the black hole is characterized by mass, charge, and angular momentum. But in the meantime, we have understood that in addition of the mass, charge, and angular momentum, already in the early 70s, Christodoulou introduced the concept of irreducible mass. It is fantastic that PhysRev letter and PhysRev research, which are two outstanding scientific journals, have accepted two letters, which I was the first author, coming back to the irreducible mass. And we have been fortunate, very fortunate, very fortunate, that the extraction of energy of black holes has been revisited. And the fortune that we had is that Roger Penrose is still very productive. And we could, since we had made a very big point in the Physics Today about the Penrose process, in the years since that paper, 71, there have been thousands of papers in the literature contending, especially in textbook, for example, in the Chandrasekhar textbook, that the Penrose process could not be operative just in general relativity. This contention that the Penrose process needed to be complementary to other concepts plagued the literature in the intervening years. And finally, in this PhysRev letter, we pointed out clearly that the Penrose process, as conceived by Penrose, it really can work theoretically. And we give the proof in this PhysRev letter article. But at the same time, in another paper, which is appearing in PhysRev report, we have shown that there are, thanks to the presence of the irreducible mass, a lot of problems how to make this process effective in science. And I was myself very astonished to find out that if you take the Penrose process as it is, there is an incredible result, namely that when you have a particle entering the ergosphere and splitting into two, one going inside the black hole and the other one coming out at infinity carrying away energy, everything is perfect. You can do that. But what happens is something which I've sensed already, but I never explicited, that these two particles, on which one goes in and one comes at infinity, have to have a rest mass much, much smaller than the initial mass. And when I mean much, much smaller, is that the initial mass of the object, when it split, it should lose 99.9% of this rest energy. In other words, the two objects have a huge kinetic energy, but very, very small mass. I was helped by Gregory Vereshchagin, who is here next to me, to understand not the paradox, but what this message means. If you have matter and antimatter, proton and antiproton, they can annihilate totally. And the energy which comes out is just in photon. And the rest mass, the mass defect, is 100%. Because all the mass, the rest mass of proton and antiproton annihilates, and you create gas radiation. The paradox with the Penrose process is that it's almost as perfect as the matter-antimatter annihilation. In the sense that not 100%, but 99.9% of the mass of the initial object are transformed into kinetic energy of very tiny particles. This is present, but not yet made manifest in the Fizerev letter. And I hope you get this point is really fascinating. But in addition of that, what we have shown in the physics reports in the other article is that if you take into account properly the reducible mass, then a new phenomena happens that when the particles split, and I said they annihilate 99% of matter, and they come out with radiation. Of course, the amount of radiation coming out is much smaller than the 29% which we expected in the early day of extracting from the black hole. Actually, without being too technical, I just mentioned the key point is that the quantity of a mass m of 100 solar mass is tiny, which can come out. But what is the worst part is that how this energy is carried away, no matter how difficult. There is another phenomenon happening, is that the horizon, this was predicted of the black hole, predicted by Penrose, increases. And the irreducible mass increase. And I don't know if Org is ready to show very quickly, I don't know if technically possible, a simulation which we have obtained. Org, there is a hope to show right now.
Yes, I can show you if I can share the screen.
Okay, let's see if it's so fantastic.
Yes.
It's so fantastic, this image, that I want you to see.
Do you see my screen now?
Yes.
Okay, maybe I have here one in this. I embedded here in this. Let me see.
Here. In red, you see the ergosphere of the black hole, and there is a white dot on the side. Is where the splitting happens. In black, of course, is the horizon of the black hole. In red is the ergosphere. Hope that you are, Gregory, enjoying also to see that. It's first time that we show. It's the first time that we show. Here you see the black hole, the white dot illuminating, which means it's extracting energy. But as it extracts energy, let's see over again, the horizon increased dramatically. And the ergosphere is just left in a small falce di luna, red. And irreducible mass increases tremendously, and the ergosphere is practically reduced. And what is the message? Is that nature does not like to have extraction of energy by gravitational interaction. And the only thing, if you try to extract the rotational energy from a Kerr black hole gravitationally, the horizon increase and is catastrophic, and the transmission of the energy of the black holes can go mainly in the irreducible mass. These are news. I could continue for hours, and we will continue today for hours. But I want just to tell you this result absolutely new.
Well, I really appreciate seeing this. It's kind of exciting, and I'm looking forward to looking at those papers. So let me know in advance when you're coming to Stanford. I spent some time this summer with Francis Everett. It was the 20th anniversary of the launch of Gravity Probe B, and so we spent a lot of time together this summer. I'm sure he'd be very interested in these results as well.
Good. Then not only negative. What we will show today is that one of the major ways to extract energy of the black hole is through electrodynamical process. We have 7 main results, but let me just mention a few. There has been, and we have still a few minutes, therefore just very, very, very short. We have been interested since 71 to the possibility of finding a black hole at the galactic center. Charlie Townes told me in September 71 at the Institute, there must be a black hole at the center of the galaxy. And I said, certainly, it's interesting. Let's see if we can detect. Charlie took that seriously. And every 10 years since, he published a paper with Reinhard Genzel. And the most spectacular technological development started because Riccardo Giacconi built the VLT in Chile, and there ESO, thanks to Rainer Genzel, made Veritas an instrument of unprecedented accuracy to look at the galactic center. He even got the Nobel Prize, Genzel, on this topic. But before he got the Nobel Prize, we published with a very, very bright student of ICRANET, Becerra Vergara, a paper that one of our dark matter model could fit this data in general relativity equally better than a Schwarzschild black hole, but the Kerr black hole could be excluded. This motivated the Nobel Committee, instead of giving for the discovery of the black hole in the galactic center, to say, if you look at the reason of the award, to find an accumulation of matter at the galactic center. We are extremely excited. Here on the left, I have Gregory Vereshchagin. We are thinking that in the galactic center, there is an agglomeration of dark matter, over which there is some baryonic matter, which we see. But in the heart, there is dark matter. And this dark matter is composed of fermions of 300 keV, and they are the structure of dark matter, not only in the galactic center, but all over the universe. This is the thing we are trying to do in this house, to identify the large part of invisible matter in the universe with fermions, and this fermion we give the name recently, yesterday, of X fermion. I would like to close on this because this opens a new era in science. And I wanted just to give you feeling and have the chance and thank Stanford for all his participation. And we will continue, of course, and we hope to have your assistance from AUI for this great adventure of ICRANET, which we started together more than 20 years ago.
Yes.